Welcome to a lesson with Dr. Powell. We're going to take a close look at continuity and limits. A curve is continuous when we don't see any breaks or jumps or anything like that, but we're going to be a little bit more precise. First, some definitions. All right, so let's suppose we have a function like this. All right, this one doesn't look continuous. Now, take a look at its range. Its range is all its possible y values. And then we're going to consider its domain. All right, its domain is everything that, everything down here, that where the functions define all the x values that you can see on the points on the graph. Now here's the new definition here, something that a lot of people aren't familiar with, the idea of codomain. So the codomain is actually, at least for us, we're going to consider it as being the y-axis. Now, it does have a, in many other settings, when we're not thinking about functions that we graph in the xy plane, the codomain actually has a lot of different things we can think about with it. But for us, we're just going to use the term to refer to the y-axis. Not all the y values are hit, but we're not trying to hit anything but y values with our functions. So the things that we're at least in the market for hitting the y-axis, we're going to call the codomain. All right. Next, we're going to have we have a couple more definitions. Image, preimage. Let's suppose we have a function like this, and we're going to take a piece of the domain right here. So this piece right here, and what does the function do? Well, it takes all these x values and pops out some y values. Collect all those y values and send them over to the y-axis and just look at them. It's kind of like a projector screen. You take something here, project it up, it's the image of it, all right? The image of this domain piece, so this domain piece has an image, all right? And that image is a piece of the range. Now notice the difference between range and codomain. Range are the y values that are actually hit. The y values that actually become images in this process. There are y values that won't necessarily in many situations, but if this function kept on going forever in that way, and down here actually the range would be equal to the codomain if all the y values were actually on the y-axis represented points on the curve. Okay, so we have image. Now what about preimage? Just go backwards. So in other words, we take a piece of the codomain, so a piece of the codomain here, and we say that because we don't want to just take a piece of the range. We're going to take a piece of the codomain in case we have situations where the function doesn't have a full range. I mean, is not every y value, but we want to be able to freely take chunks and pieces of the codomain, parts of the y-axis, and think about their preimages. So if we cast it, in this particular case, when we cast it down, the preimage is kind of like the shadows of all the y values that are actually hit, but in terms of the shadow is cast on the x-axis. So all the x values that are actually sent up with an image that is in that interval. In the situation where maybe your function's like this, maybe it stops right there, and let's suppose we have a codomain piece, and I'll just represent it like this, so a codomain piece in here. What would its preimage be? Well, its preimage would be the shadow cast by all of the points that are actually, by all the y values that are actually in the range in that piece. So right here, from here to here, just the shadow that's cast there. If this was on the x-axis, it would just be that shadow. I mean, the y values up here won't cast any shadows, and that's okay. Just the ones that do. If we happen to have a codomain piece where the function didn't even go up into it at all, then the preimage is simply empty. It's the empty set. It's nothing. Okay. So, but in general, this is a nice term to use. Preimage from a codomain piece. It's all domain pieces that map. So using the idea of mapping, well, kind of like an image projector, we're going to use the word map to mean like sent to or come up to the image, right? Everything, all domain pieces that map into the particular codomain piece that we chose in order to find the preimage of it. So the preimage of this codomain piece in particular is this shadow, those shadows that are cast. Okay, so continuous, what does that mean intuitively? Basically, it means if you change the input just a little bit, that's going to create just a little change of the output, right? Because as we're drawing a curve, right, as we move this way a little bit, we don't want to be, we don't want to like rapidly jump up somewhere, right? We don't want something like that to happen. Now, continuing on, but how small does the input change have to be to make a small output change? Because we kind of want small input makes a small output. But in this situation right here, see this curve with a steep slope or downward slope right here, just a small input change between this point and this point, just very small. But look at the big output change. All right. So we need some precision in order to make this idea more clear. Okay, suppose we'd like to like only a small output change. I'm going to call that fuzz, some fuzziness. Okay, some small output change. In fact, we're going to not just think of it as being possible outputs, but in kind of the target marketplace of outputs, the codomain. So we're going to take fuzz in the codomain. So we're going to take some fuzz about a point, just up and down just a little bit, and we want to know, is there an input change, and in fact maybe even fuzz around a particular point, that's small enough to permit just only a small change in the output. So for instance, like how small do we have to go so that so for instance, if I have a curve and maybe I'm thinking, okay, permit just this small change. Suppose that's the change I want, some fuzziness here in the codomain. And how small do I have to be? It looks like in this particular case, you can just look at the preimage of that fuzz and you'd get it, right? If you're just in there, then you'd end up getting in there. A small change here would be a change there. All right, so kind of what we do is we say, is the preimage of some codomain fuzz fuzzy? Is it a collection of fuzzy spots in the domain? That actually is one definition of continuity, which is a little bit more precise, but I mean, that sounds pretty fuzzy, and doesn't sound very precise. Let's keep going here. So the codomain fuzz, all right, here's an example of why that definition might actually be a nice one to use. I mean, if you take a look at some codomain fuzz here and look at its preimage, its shadow cast, notice that it's not exactly fuzziness. Now, for us, we're going to think about fuzziness as being something called like an open interval, like from A to B on the number lines. So if you have open point, and just everything in between, not including the endpoints, that's one way of thinking about fuzz. Fuzz is kind of a fun word though for now. Okay, so the preimage of this codomain is not fuzz, is not going to be fuzz down here. It's not going to be an open interval. So this is an example of saying, well, wait a minute, this function with the jump is not continuous, right? It doesn't satisfy that criterion that the preimage of fuzz has to be a collection of fuzzy spots, or kind of like a union of fuzzy spots. All right, so like I said, fuzz is like an open interval. Codomain fuzz, let's take something in the codomain. Now, the way we're thinking about it as an open interval, it has a center. Let's just call it L. And epsilon, this is a Greek letter. We're going to let it represent a small positive number, all right? It's going to represent just a little distance up and down from the center. We could even notate it like this, L plus epsilon, L minus epsilon. And what we're saying is the preimage of this codomain fuzz, this open interval, like going up and down epsilon. All right, we want to take a look at that, and what we'd like to say is that the preimage is, we want it to be a collection of fuzzy spots. But first we need to like try to come up with a description of what the preimage of such an open set looks like. Well, it's going to be all x's, so all values of x, so that f of x, which is like the image of a particular x, right? Take an x value, its image casting up onto the function, the y value it's going to get is f of x for one point, right? The image of f of x. So we want the image, so all x's so that their images, so f of x itself, is actually in there. That's a description, just another way of saying what the preimage of this guy is, the shadow that's cast. So how do we know when f of x is in there? How do we know that something's actually in the preimage? Is there a condition that we can write down that would guarantee that? Let's just think about that for a minute. So at the picture, all right, so we have L, epsilon going up and down. Let's take a point here that the function's actually hit, a y value is hit by f of x, the image of x by some point, all right? How can we guarantee that f of x is actually going to be in here from up and down? Well, let's see. The distance between the center, L value of this codomain fuzz, and f of x, well, that has to be less than epsilon, right? The distance between f of x and L has to be less than epsilon. Now, how do you find distance between two things, two numbers? You subtract them. That finds the distance. As long as one is like bigger than the other, that works. But if one's smaller than the other, just take the absolute value, make it positive, and it works. The absolute value of the difference of two numbers is the distance between them, no matter which one goes first. It doesn't matter. So just saying that this distance is less than epsilon guarantees that our x value will be in the preimage of this codomain fuzziness. All right. So all x's such that absolute value of f of x minus L is less than epsilon should be a collection of fuzzy spots. So kind of what we're trying to say is that fuzz in the codomain, all right, will come from fuzz itself. It can only come from fuzz. So saying a preimage is like where have y values come from? The places where they have come from is fuzzy. All right, that's their description of what continuous means, right? So just small changes around in the input will only make small changes in the output. Now, in particular, this is kind of important. Every value, every point on the x-axis that's actually in a fuzzy spot, like this, or in an open interval, there's actually a smaller open interval that it's contained in. It's kind of neat. No matter how close you get to the end right here, there's always going to be a small thing where it's contained in, where it's actually the center of a fuzzy spot. So if we go off a particular distance that way and that way, I'm going to use a Greek letter. This is delta, lowercase delta, Greek letter, and we're going to let it be a small positive number going, this way or that way. So what we want is we want the image of this guy right here, x minus delta, x plus delta, to be completely contained in the codomain fuzz. So we just need delta to be small enough. So pretty much this is what we say, all right? If for every y value in the codomain and epsilon greater than 0, what does that give us? That's a distance. That gives us codomain fuzz. Basically, for every bit of codomain fuzz, we're going to look at its preimage. How do we describe its preimage? Let's see. Well, we say if x is in the preimage, all right, so we're going to look at the preimage, I guess, and see if it's fuzzy. So if x is in the preimage, then there exists a delta, so a little distance away from x, if we go to the left and right, like this, that this bit of fuzz is actually in the preimage also. That actually guarantees that the preimage is fuzzy, really, because every point itself in the preimage will have fuzz about it that's in the preimage. That actually guarantees that we have an open interval. I mean, it's kind of like this. If we have okay, so if we had where this didn't happen, like what if we had something like this, right? Well, this point right here, there's no bit of fuzz that'll be completely contained in this set right here, because fuzz will always take you outside of it. So this is an example of you know, that idea of centering that we just looked at right here not working, right? Essentially, if we have this centering idea of working with every single point in there, we actually know it's a collection of fuzziness. So that's enough for continuity, all right? So now we're going to be discussing here what it means to be continuous at just one point, and we will save that for the next video. So stay tuned, because we're going to have a little bit more description here to come. Thanks for watching.